Okay. Good afternoon to all. Uh, so welcome to this live interactive session, and for this course, mathematical modeling of the manufacturing processes. So let us start with this interactive session. So I have already gone through this forum as well as this Excel sheet, which you are supposed to interact with this me, basically the instructor of this particular course. Any query with that? But unfortunately, I have not received anything your side. Maybe let us discuss by just looking into the aspects which may be more important related to this particular course. Maybe having some difficulty in understanding the content, very particular topic related to that supposed to discuss. Apart from this, still have some query. If you can type all your query in the chat box that answer answer them. Anyway, I think let us start with this discussion on the. I'm just trying to share with the PPT, and from there we just discuss selective topics related to this session. This course, mathematical modeling of manufacturing problem. I hope after going through the details of this already you have covered the 3 modules, and you have at least you understand that the content of this particular course specifically focus on the different mathematical aspect of this particular course. This mathematical modeling of manufacturing process. So now, basically, we are discussing this part, that content of this course. So here you can see that course content is pertinent to this. First one is the module that is the introduction to manufacturing process. Then physics of manufacturing processes and conventional. These are the 3 things I hope so far we have covered using uh, in this courses. Now, introduction to manufacturing process. We have very basics, fundamentals of the manufacturing process, such that so mathematical aspect related to the manufacturing process. We want to understand that was the focus actually of this particular module. Second one, what are the physical phenomena associated with the manufacturing process? First, to understand the mathematical concept on applied mathematics related to particular subject, to understand what are the physics involved in the manufacturing process. That is the module 2. And third module is the conventional machining process. So conventional machining process, here you can see that in conventional machining process, we can see uh, that how we can construct the marching cycle diagram, because this is the basic part of the conventional machining process, making the assuming the equilibrium condition, the balance condition. Here we can find out what the different component of the force they make the balance, and looking into this balance force components, we can find out which is known, which is unknown from there. So is it's a very easily you can find out what are the different components of the forces and correlate the parameters associated with the conventional process. But if we look into this, okay, so these 3 processes we are supposed to discuss, since we have not raised any kind of a query related to this particular topic. So I'm just doing the selective part of this thing. But before that, try to look into the references, because this is very important. So maybe looking into all these class notes, PPTs, or maybe lectures, videos help you understand the subjects of overall idea of the subjects. But if you want to go in depth in details about the different process. Different differences are very important, significant. For example, very mathematical aspect, if you want to understand, then you definitely should go for the first book, that is the Professor Ghosh and only manufacturing science. This is a very standard and very precisely describe the different types of the manufacturing process from the point of view the different mathematical aspect, their application, what it implies, sample calculation, and at the same time some solve problem are also there in this particular book. So you'll be able to understand the different kind of the mathematical problems associated with the manufacturing processes. That's why I keep the very first reference, that is this manufacturing science. If you go much details interested to metallurgy related to metallurgical aspect, maybe metallurgical fundamentals, reference is significant in this case. Third references, you want to understand the plasticity, different plasticity model, and that the manufacturing process, mostly related to the metal forming processes. Very fundamentals of the plasticity, if you want to understand, then probably you should follow this book, third, even fourth book also. There also you can get the theory of plasticity. This is very fundamental books and more or less different elasticity theory and the different plasticity theory. You will be getting much details references 3 and 4. And nowadays, it's a very important to understand the micro scale processes. Maybe if you are interested to look into different micro welding or even nanoscale joint processes, then the fifth reference book is very important. Apart from this thing, related to the only welding process, go to if you want to understand the principle of the welding processes, different types of welding processes, and then reference 6 is the most significant. And in general, overall idea about the different manufacturing processes, heat treatment technology, or other relevant production technology. That is, in that case, the reference book 7 is more important. So in that case, we can follow this book number 7. And non-conventional machining process or advanced machining processes. And that book number 8, so VK join, that book is very important. So very significant for this particular. And even focusing on the very micro manufacturing technology or different aspects of the micro manufacturing or fundamentals of micro manufacturing, then reference 9 is important here. And finally, if you are very much interested in additive manufacturing technology, so in that case, probably book number 10 is more significant. Fundamentals of solidification will be associated with the casting process or associated with the welding process. In that case, the reference 11 is the more significant in this particular case. Now, I just selectively try to understand the maybe few topics. That is one of these, the principal stresses, and that normally cover in the physics of the manufacturing process. Although we have gone through the lectures, everything slides are also here, and at the same time, maybe you have solved the assignment problem. But sometimes to understanding principal stresses, very simple, only two-dimensional cases, it is very important. Now we have seen that the state of the stress can be expressed in general way, that define the x-axis and y-axis, assuming that different stress components are acting. Now, sigma x and sigma y are the normal stress components, and along with the shear stress, tau xy is acting in this case. Now, how you can estimate the principal stress, even if you know initial state of the state, sigma x, sigma y. Therefore, principal stress can be estimated simply looking into this thing, because in general you express the stresses as a function of the orientation different, because for example you orient the state of the stress at a different angle, then orientation, that which cases will getting the maximum or maybe optimum, and find out sigma y d theta. Definitely sigma is the state of the stress, can be expressed as a function of theta. Finding out the d sigma y d theta equal to 0, make it as a 0, then we can get some condition. That condition you will find out what are the state of the stress, that is called the principal stress. It's not necessary that principal stress will be in the same direction or the same uh, as well as the in which the actual original state of the stress, that means, or we can say the initial state of the stress is acting. take an example, say initial state of the state sigma x is acting along x-axis, y is acting along y-axis. Now principal stress can be between this thing with a certain angle with respect to x-axis. Along that angle, there is principal stress is acting one direction, and then perpendicular direction, another component of the principal stress is acting. And now what way we can estimate this principal stresses? So here you can see the principal stresses. The average stress can be simply represented by sigma x, sigma y. Right? Remember, sigma x, sigma y, the initial state of the stress acting along the x-axis and y-axis respectively. Now from there, you just making an finding out their slope equal to 0, d sigma by d theta equal to making this 0. So there are say for example at a particular angle theta p, the plane of the principal stress is acting. So there the plane of this plane is defined, the relation of this thing, the tan theta p equal to tau xy. This is the initial state of the shear stress value. Sigma x, sigma the normal stress value. So from here we can find out what is the theta. Then we can define this plane of the principal stress is acting. So theta p means, for example, one angle with respect to x-axis, say theta p1, one state of the principal stress is acting, say sigma 1, and another, say theta p2, another angle, but that is 90 degree apart with respect to theta p1. So there also another state of the principal stress is acting. Now, in principal stress, in the principal planes of the principal plane, there is no shear stress is acting. So therefore, here you can estimate the sigma 1, sigma 1 equal to, say for example, sigma x plus sigma y by 2 plus root over of sigma x plus sigma y by 2 square plus tau xy square. So this is one, and sigma 2 corresponds to take the negative value. So sigma x plus sigma y by 2 minus of the. So like that, we can find out the stress component sigma 1 and sigma 2. Similarly, we can find out the plane of the maximum shear stress. Say, suppose the angle is theta s. So from here, the similar relations we can find out tan 2 theta is equal to minus of sigma s minus sigma y by 2 divided by tau x. From here, we can find out what is the value of theta s. Say, for example, theta s equal to theta s1 taking as a reference, and theta s2 is the say another angle. There is the plane of the maximum shear stress. So theta s1 and theta s2 are the 90 degree apart. These two angle, the shear stress is basically plane of the maximum 90 degree apart. But as compared to the principal plane, that is the actually the angle the principal plane and the maximum shear stress is 40 degrees opposite. So we can get this expression of what is the maximum value of the shear stress and in plane maximum in plane shear stress value, that this component and maximum shear stress is basically the amount of sigma x minus sigma y by. So this we can estimate. Now principal stress component, suppose it is a three-dimensional system of stress, then how we can find out the different principal components? Then we can follow the very simple calculation. So the axis is transformed, so that means if you got the relation that different way the transform the axis, and that particular axis with respect to the reference value of x-axis, there you can find out what is the value of the principal plane and what is the value of the principal stress. For three-dimensional state of the stress, we can use this, look into this characteristic equation. Say for example, x is the variable here, a to x equal to lambda into x. This is called the characteristic equation of the stress. So A represents the 9 component of the stress value. So 9 component of the stress value means here you can find out the 3 normal stress components and remaining are the shear stress components. Now Ax equal to minus lambda I x equal to x. So this simply performs metric operations, and then from here you can find out the A minus lambda I. I is the identity matrix here into x equal to 0. So therefore the principal stress value, so from the once you form the characteristic equation, then determinant of A minus lambda equal to 0 from there, and it means that A minus lambda equal to 0. So therefore the stress component into n equal to lambda n. So this expression we can find out from there, this characteristic equation. By solving this equation we can find out the value of the principal stress. So it takes this form. Say identity matrix is there. For example, lambda is the say kind of variable in this particular case, or maybe root of this particular equation. Now once you determinant of A minus lambda equal to 0, if you perform this exercise, then we can find out the sigma 1 minus lambda, sigma 2 minus lambda, sigma 3 minus lambda. And here this sigma 1, sigma 2, sigma 3 is the normal stress component. Sigma 1, 2, sigma 1, 3, these are the shear stress component. And we are assuming this is symmetric because there is no rotation is there, so that in that case we can assume that is a symmetric state of the stress. So then if you do deterministic, you can find out, then you convert to do this thing, this in the form of equation, then it basically finding out the cubic equation. So once you solve this cubic equation, the roots of this cubic equation represents the principal stress value. So here, but you need to solve this cubic equation. So for example, finally you can convert this thing as a cubic equation, that is the lambda q minus I1 lambda square minus I2 lambda minus I3 equal to 0. So here I1, I2 and I3 normally called as the stress invariance. Now this root of this equation, so this, for example, values of the lambda 1, lambda 2, lambda 3, that actually represents the principal stress value in case of three-dimensional state of the stress. Now this equation is independent of the orientation of the coordinates. Definitely it's independent what kind of orientation can follow. It's independent of the orientation of the coordinate system. So once you solve the values of the, say, lambda 1, lambda 2, lambda 3, or sigma 1, sigma 2, sigma 3, that represents the principal stress components, and accordingly the principal direction equal to n1, n2 and n3. This is the eigenvector problem. So therefore three orthogonal plane coexist here where there is a no shear stress, that is that orthogonal plane represents the principal in case of three-dimensional stress. Take an example also. So for example, find the stress invariance and the principal stresses to the principal coordinate system using this particular tensor. So suppose sigma equal to this state of the stress is given. So here we follow the same thing, similar way, that form the characteristic equation, and from there you can form this cubic equation, solve this cubic equation, find out the roots of this equation that represent the principal stress component. But how you can find out? For example, first, if you can find out the first root of the equation, for example, some predictive techniques, say Newton-Raphson method, you can find out the first root of the equation. Once you get this thing, then that quadratic formula you can apply. From there, we can finding out the other two roots of this particular equation. So here, the different components of a principal stress. When you're analyzing this thing, we're representing the cubic equation, but if you see, there are three components, the I1, I2 and I3, that actually represents that is called normally the stress invariance. So it have the particular form. So say for example, I1 equal to sigma xx plus sigma yy plus sigma zz. Similarly, I2 and I3 have particular expression, but here sigma xx, sigma yy, sigma zz, the initial state of the stress along the x-axis, y-axis, z-axis it is acting. But it's not equivalent to the principal, because principal plane are different. It's not exactly the principal stress may not act along the x-axis. It act in some other direction. Now the same, once you finding out the principal stress, sigma 1, sigma 2, sigma 3, the stress invariance can also be represented in terms of this principal stress component. For example, in this case, I1, I2 and I3 can be represented in the form of principal stress components, 1, sigma 2, sigma 3. Actually, this stress invariant is somehow very significant or important to calculate the different components of this thing. Now, that is a way to we can, the different kind of the stress state we can explain. But apart from this thing, we can find out the hydrostatic and deviatoric stress components in case of, for example, two-dimensional. So any state of the stress can be represented in the form of a hydrostatic stress and deviatoric stress component. So here you can see the hydrostatic stress components actually cause the elastic volume changes. So there is a change of the volume, not the plastic deformation, but the deviatoric stress components is basically can be represented also, and deviatoric stress component is maybe responsible in some other action. So maybe shearing action is important in using the deviatoric stress component. So then when you tighten the yield process, the yielding process, when this is actually independent of the hydrostatic state of the stress. So therefore, however, fracture stress is strongly affected by the hydrostatic stress. So different kind of a theory may exist, but point is that maybe some cases when you try to analyze the plasticity model, in that cases maybe we need to know the concept of the hydrostatic stress and the deviatoric stress components. But just to know here that any state of the stress, here you can see that it can divide into the two component. One is the hydrostatic part and another is the deviatoric stress component. For example, sigma xx, sigma yy, tau x is the general representation is the two-dimensional stress state. Now I am trying to divide into two components. One is the hydrostatic part, another is the deviatoric part. So hydrostatic part is that it's basically it's acting is the equal amount of the stress. For example, sigma xx, sigma yy, they must be equal. So in this case, but sigma xx not sigma y not exactly equal, but we can say that rather it is acting some average stress value. That is the mean stress or average stress value, the sigma xx plus sigma yy by 2. So here sigma n and sigma m. So both are same, both are the same value, and other are zero component. So this is the hydrostatic part, and remaining part is the deviatoric part. So here sigma m minus sigma yy making the balance of the sigma ij. So remaining part is the deviatoric stress component. So this way we can separate any state of the stress in the deviatoric and the hydrostatic component. Similar is applicable in case of the three-dimensional state of the stress. In this case, hydrostatic pressure or state hydrostatic stress can be the average of the sigma 1 or sigma 2 to sigma 3 3, or we can say that is a I1 by 3. I1 by 3 means the first stress invariant I1 divided by 3. Here you can see that sigma p is all the same that same value. The hydrostatic stress remaining such 0, no shear stress components here. But deviatoric stress, the remaining part of the stress is the deviatoric stress component. So that's why sigma equal to sigma h plus sigma d. It means the hydrostatic stress and the deviatoric stress components we can define. Means that the existence of the sigma p, that means hydrostatic pressure or hydrostatic stress, does not alter the principal direction. It is true, cannot alter the principal stress direction, but it does not contribute to the shear component. Only the so that's why even if we analyze we can finding out the other way also. For example, let us look into this thing. Try to finding out what is the principal stress value. That can also be considered only just looking into the deviatoric stress component. So therefore, sigma d minus lambda I equal to 0. So the characteristic equation, and from this equation we can form this cubic equation we are getting, but nature of the cubic equation is something like that: lambda minus I2d lambda minus I3d. So I2d is the stress invariant but corresponds to the deviatoric component. So therefore we can handle the stress invariant corresponds to the deviatoric component, because if you look into the deviatoric component, the first stress invariant I1d, that is actually equal to the 0. So from here, if we solve this equation, then we can finding out what is the value of the principal stress components. Then that value corresponds to principal stress component, but that corresponds to the only the deviatoric component. But if you along with the deviatoric component, if you add the hydrostatic component, then it becomes the actual principal stress value. So this way also you can consider finding out the value of the principal stress component from the deviatoric stress part. Now, sometimes some point of time we just try to discuss what is the von Mises-Ill criteria. For example, you know that in uniaxial tensile testing model, so there we can finding out the Ill point value is a single point value, because there is a uniaxial tensile testing. But when the multi-axial three-dimensional state of the stress is acting, then how we can define the Ill function? So it can be a Ill function that can be a involve all the three principal state of the stress component. So that is the sigma 1, sigma 2, and sigma 3. Or this yielding can be represented, this thing, it's a yield surface can be represented like that. Say for example, k equal to sigma 1 minus sigma 2 square plus sigma 1 minus sigma 3 square plus sigma 3 minus sigma 1. So that means all the three components are equal. It's basically define the yield surface. But this first function is in the form of a the sigma 1, sigma 2, that means in the form of a principal stress component. But second one is the form of the original state of the stress. Now this factor 1 by 6 can be included in the different arbitrary constants. So this particular functional form is known as the von Mises-Ill function. So here you can see that this actually, if you look into when we discuss how the von Mises-Ill function, there are with the several assumptions and different conditions, then we can find out that it actually a function of the yield surface is function of only the second stress invariant, deviatoric stress invariant. So I to D. So that's why that represents the actually functional form of the yield surface. Now this is well known von Mises-Ill function, but how you can utilize this functional form in the different cases. For example, suppose you are analyzing a two-dimensional. So two-dimensional you can easily convert to from three-dimensional principal stress component. The K is the basically representing the yielding function. So K functional form. k equal to in terms of the two-dimensional space, simply making the sigma 3 equal to 0, then it represents. So it represents the sigma 1 minus sigma 2 square plus sigma 1 square plus sigma 2 square. Now this is the data. Now from there, you know that uniaxial tensile testing, you have the data and you can single point the where the yielding start basically. So from that you can define from a uniaxial tensile testing sample. So now in particular cases, if you follow the uniaxial tensile technique, only one principal stress component is there. Say sigma 1 equal to sigma bar, for example, this is the stress value. But in other cases, sigma 2, sigma 3 equal to 0. Put this condition here, then you can see that k equal to some value twice sigma bar square, or finally sigma bar equal to root over of k by 2. Or k you can replace the k in terms of the sigma bar square. So sigma bar is basically defined quantity, because sigma bar represents the yield stress value that when you are performing the uniaxial tensile testing. So from there we put the value, we replace the k in this particular form, then we can say sigma bar in terms of the sigma bar equal to this. So that represents the von Mises in case of two-dimensional cases. Now suppose you have the option to look into the biaxial tensile testing, you are performing this kind of experiment. Now how you can utilize this yield surface? In this case, the condition, the biaxial tensor means sigma 1, sigma 2 both are same, equal to sigma bar, but sigma 3 equal to 0. Here also you can find out the sigma bar equal to root over of k by 2, or other way k can be replaced in terms of this thing. But remember, this data sigma bar, this value you are trying to obtain by in case of the biaxial tension. Similarly, suppose performing the testing the sample in case of the pure shear condition, but mathematically pure shear condition exists if you the principal stress sigma 2 equal to minus sigma 1 and sigma 3 equal to 0. From there we can find out some relation what is the value of the sigma bar. So that is the root over of k by 6. So it means that different, for example, you are representing the sigma 1, sigma 2 axis, the two principal stress axis. Now that is basically this kind of ellipse, equation of an ellipse, represent the ellipse, then this point indicates that biaxial, the k by root over of k by 2, this point represents the uniaxial tensile data, and then it represents the shear, pure shear condition, this point. So therefore sigma 1 sigma 2 represent the axis, the major axis of an ellipse, and then we are graphically represent this thing. So that means this actually indicates the in general the functional form, until unless you are not defining the what is the k value, then it's a general, this is the functional form of this thing. So different values of the k, this can be, it can be a different shape, but actual shape is the ellipse, then major and minor axis can be different. But if you have the different data, if you perform the different way, the uniaxial tensile testing, say biaxial tension, pure shear, then different points you can define on this axis, and accordingly you can utilize the data. So similarly, the shape can be represented like that, some equivalent form, equivalent state of the stress. It means that all three, that equivalent, you are trying to represent the single component of the stress, which is a function of the all three principal stress value. Now if you follow the von Mises yield criteria, yield surface, then that equivalent form of the shape can be represented the k equal to the sigma 1 minus sigma 2 plus sigma 2 minus sigma 3. But this is the way to define this yield surface. Now if you see, say this is expression is like that, sigma bar square equal to half is factor is coming because you have that, you're utilizing the tensile test data. Now sigma 1 bar, say now it says how yield surface evolves during the deformation, the yield surface, because of strain hardening effect, the yield surface evolves from first initial yielding start at point sigma 1 bar, further you're deforming, then it goes to the sigma 2 and 3. So this kind of, basically we can say the isotropic hardening model you just incorporate through the term k here. So accordingly we can represent the how the yield surface evolves in a deformation process. Okay, so this is the other part of this thing. Maybe you find out some difficulty to understanding this thing, physical modeling approach. So definitely, although in this particular module we have tried to look into the different analytical models, so basics of the physics and the mechanics of the metal cutting, and try to looking into the different mathematical representation in analytical way. But at the same time, it is also important that how to look into the different other numerical model, because analytical model involves a lots of assumptions. So then in that case, maybe so far you have gone through the conventional machining process. So there also you can apply to develop the numerical model using finite element method, finite volume method, and even finite difference method can also be applied. But in this case, first you have to define the domain, have to decide where you want to analyze these things. Say you want to do in general the deformation analysis or maybe heat transfer analysis. That kind of analysis you have to decide first. Then first decide the solution domain, then discretize the domain. For example, if you took an finite element, discretize the domain associated with the workpiece, basically the solution domain. Now formulation can be like that. Say deformation can be either Eulerian approach, you can follow a Lagrangian, arbitrary Lagrangian Eulerian approach. If you follow in standard software also, all the modules are available. So what kind of the approach you want to follow? Now which cases we can do? Eulerian approach, what we can do? It's a basically Eulerian approach that grid is fixed. So that means your grid, you discretize the domain and then it creates number of nodes, elements. So node point are fixed basically. But how you can define the variable? Because each and every node point you are defining the variable is defining the velocity field like that. So that is the Eulerian approach. So material flow through the domain basically, but domain is not moving. So domain you can keep as a fixed. Now this type of approach, it is free from any kind of the element distortion. Basically you are not allowing to deform the element. So element or nodes are fixed position, it is there, but you are not allowing to deform. Only you are representing the certain is passes through this node and you are representing in terms of the kind of velocity field on the particular node point. So that's why in this case no remeshing, that means is not required. So therefore when the fixed domain is there, but it's a computational time is normally low in this particular approach. But if you look into the Lagrangian approach, here elements actually deform when you deform during the cutting. So some sort of it follow the deformation. But in this case, maybe more appropriate in case of the metal cutting simulation, because in this case the unconstant material can flow from because chips is developed and chip is continuously flowing through the domain. So therefore some point of time you can allow the deformation of the mesh. But the computational point of view, in this case the remeshing, that means once the one particular node deformed to a large, then we are allowing the remeshing and then again meshing of this particular domain, and the transformation of the variable each and each node point previously to the new node point. That may be the difficulty, or maybe they need to compromise with the accuracy of the results. At the same time, it's a more accounting is required in this particular process. It means that it's computationally more expensive. So that's computational time is large computational time will be involved in Lagrangian approach. So, but maybe in some, depending upon the problem, maybe in the metal cutting process, the Lagrangian approach, even it is computationally expensive, but maybe required also to understand the different physical aspect associated with this metal cutting process. Now there is often you use that in the standard software, you use the ALE approach. So arbitrary Lagrangian Eulerian approach. So by taking the advantage of the both Eulerian and Lagrangian approach in these cases. So in these cases, either mesh can be moved arbitrarily related to the workpiece, but it can be option have the either taking this advantage. For example, taking the can be reduced to, can use either Eulerian approach or you can follow the Lagrangian approach. Take an example also that Eulerian approach is followed near the tool tip, because this is almost fixed boundary. So here you can finding out the tool tip, the Eulerian approach is more important, fixed boundary. But Lagrangian approach is required to follow the flow of the material at specifically the free boundaries. The free boundaries we try to look into the approach of the Lagrangian. So that's why taking the advantage of the both Eulerian and Lagrangian approach is normally followed in ALE. Now, apart from this thing in general, if you try to analyze the different physical model also, that stress, deformation behavior, all things are maybe when you try to heat transfer analysis, then you need to standard heat conduction equation to get the temperature distribution. Even if you want to do stress analysis, then you need to know a deformation behavior relation between these two. For example, a relation between the stress, strain, and distortion also. So how they are related to using some constitutive equation, how it relates. We need to know that kind of equation, then we can apply all these things. For example, some material behavior. So steel normally behave, it's having the elastoplastic model material behavior. It is like that metal, because we know that any metal which deform is there, some part will be the elastic part will be there. Even elastoplastic material means you remove the load, then some elastic recovery will be associated with these things. So therefore, in that cases, material behavior can be considered the elastoplastic behavior. And apart from, there are several plasticity model also if you want to deformation analysis. So you need to understand that what are the different plasticity model. But normally you can use the von Mises-Ill criteria condition. You can use this thing, and we normally use the isotropic hardening. All kind of, even you can use the kinematic hardening also, but in that cases model will be more complicated. So these are the basic standard elements, terms, terminology you can use when you try to develop the physical model of the machining process also. Apart from this thing, we can develop the plasticity model assuming the strain rate dependency, that also, and most general we can use the in standard software the Johnson-Cook model, because Johnson-Cook model is more versatile in the sense that all the variables are there. Maybe this Johnson-Cook plasticity model, here you can consider the strain component, need to consider the strain rate also, you need to consider the temperature also. So it's a model is a function of the strain rate and temperature. All you can incorporate, making the more reliable model of the material model associated with the deformation process of specifically talking about the machining process. Now already mentioned this thing, if you want to do the heat conduction equation, then temperature distribution is the most suitable there. And then after that, material flow can be considered. In that, normally you can use the fluid mechanics approach, these things. And apart from this, okay, so I think that's all to understand the different few topics I just discussed. And thank you very much for your kind attention. So maybe if you need the more interactive section, maybe another 1 month we'll meet again, once again. So at that point of time, we'll try to discuss the very selective topic related to so till now. So thank you again. Thank you for your attention. Now we'll try to discuss that related to anything you want to raise in the chat box. We'll try to discuss that part now. So I think no, till now I didn't see anything posted on the chat box. Any query? Okay, I think till now, so maybe I can stop here, and I think may not be required. Maybe I can stop. So thank you very much for your kind attention. Maybe our next live interactive session will be discussing more, and I think at that time probably you'll be going through much more modules, and probably you might have some query at that time. So that's all. So thank you very much.